Stanford University.
The last factors of 2, 3, 4, sometimes just 10, 20% out of your GPU, the current generation and hopefully also the future generations. And so before I tell you anything more about what works, what doesn't, and what you have to pay attention to, this is the most important thing I can tell you about optimization and performance tracing. Always measure everything, even if it's very obvious. You think you know everything. It might be more complicated than you think. So always have a good timing infrastructure in place so that you can measure accurately and precisely what's going on, where the time is going, and that you can always also compare prior versions to later versions, which you have hopefully optimized more, because sometimes there's weird interactions that you've optimized part A, but somehow you introduce a subtle change which somehow is causing part B to run slower. It has happened, and then your part A is running 10 times faster, but part B is running 5 times slower, and part B was much bigger to begin with, so it's a net negative. So for those reasons and many more, measure. And the second thing is, don't over-optimize small pieces of your code. This is kind of one variation of Amdahl's law. If a certain chunk of your code is taking 30% of the time of your overall program in the beginning, and you make it 100 times faster, well, great, but your code won't run faster than 1.5x because you've just cut effectively 1/3 of your work. So once you've optimized a piece of code or a piece of your program, and it's taking a very small amount, then look at what else is remaining. And even though often you start with things, well, that's completely unimportant because that's 2 to 3% of your overall execution time. After you've probably parallelized and optimized some piece of code which took 90-something% of your time beforehand, that remaining 2 to 3% will be 50% or more of your execution time. I've seen it happen to friends, I've seen it happen to myself, where we just kind of get used to, this is the one piece of code we have to care about in the whole program, and then you come back like a week later and you're like, oh wait, just reading and writing files is now 50% of my overall execution time. I should have stopped 3 days ago because I was doing work which has very little return. So always be aware of those things. Know where your time goes and know why you're investing effort and time into optimizing things. And know when it's time to move on, and know when something is good enough, or it's now okay to go look for new and better algorithms or new and better workloads, or just try to do something completely radical because the current way of doing it is kind of played out and you can't push it further. All right, so with that said, I'm going to talk about kind of these general topics today. Memory coalescing is the fact that when you read and write from global memory, which you've been doing basically exclusively up to the examples we've showed you of shared memory, even though you want to read, let's say, a single float or int, which is 4 bytes, the hardware actually will be reading a whole chunk of memory. And so if you are not aware of that fact, you can waste a lot of effective bandwidth in the hardware. And second, if you make a bunch of requests and they're all over the place, then the hardware has other problems besides just wasting lots of bandwidth. Then shared memory bank conflicts. So we told you last time about how great shared memory is. Unfortunately, there are a couple of things you need to consider. In particular, the hardware for shared memory is subdivided into banks, which is basically, let's say the first kilobyte is in one bank, just as an example. The second kilobyte is in the second bank, and so on. This is not actually how it works, but just as a simple example. And if multiple threads in the same warp make requests to the same bank in the same cycle, in the same instruction, then only one can be serviced at any given point in time, so you will slow down. And I'll show you some examples of how that works and how you can get around that. So control flow divergence, I talked a little bit about a couple of lectures ago in terms of if statements and switch statements. Here I'll just go into just repeat that a little bit and talk about loop divergence in terms of that you'll have that one thread which needs to execute a loop like 1,000 times, and everybody else needs to execute it 100 times. And that one thread will drag along everybody else, and you will kind of be wasting a lot of time and hardware. And lastly, I got into this kind of tricky issue of occupancy in kernel launch overheads with some illustrations. So, memory coalescing. Memory is accessed in chunks. The minimum chunk size on current hardware is 32 bytes, right? So that's effectively 8 times the size of a single int or a float. So if you say, I'm going to go access some piece of memory from every thread in some random order, you think you're reading in 32 times 4 bytes, but the hardware is effectively reading in 32 times 32 bytes, 8 times more. If you read in everything in a way where all the threads are reading out neighboring values, in an array, you're actually just reading out 128 bytes. So you're 8 times more efficient. And if you're bound by, you access reads and writes to memory, to global memory, you will probably run 8 times faster. So, and the second thing is these chunks are not just random 32-byte chunks or 64-byte or 128-byte. They are aligned, right? You're starting at 0. The chunks are directly of nice multiples of 32. So what happens is even if you are accessing something with a contiguous chunk or portion of memory, if that portion happens to be kind of overlap to chunks of 32 bytes or 64 bytes, what effectively will happen is that you'll read the first, let's say, 64 bytes and the second 64 bytes, and you'll throw away some part of the first one and some part of the second one, and effectively you'll be using twice as much memory bandwidth as you think you are. So just kind of as an illustration, so let's say you're accessing pretty contiguous portion of memory here, with T0 starting somewhere around 100. So you think, well, you'd read out 128 bytes, but the hardware is actually smarter. It says, well, I'll read out these 64 bytes, starting at byte 64 up to 128. And, oh wait, I have some more requests I need to fill. So actually I can even cut off, because there's nobody in the range of 64 or 96, I can save some and actually only use 32 bytes of bandwidth. And then it does the same thing kind of on the second part. So it says between 128 and 192, how many requests do I have? And it says, well, I have requests kind of in both 32 byte chunks, which make up those 64, so I'm going to just load the whole 64 bytes in. So kind of getting back to the code you're used to, if you are accessing arrays, and up to now we've mostly done it this way, you calculate your thread ID, your global thread ID, and you just access some array in this fashion, right? This is optimal, right? You're going to use exactly as much memory bandwidth as you think you are, and the hardware will give you the maximum amount of throughput that it can. If you are accessing something with a stride of 2, right, so that you're accessing all the even words and leaving out all the odd words, well, effectively, the hardware will say, I'm going to load up twice as much, use up twice as much bandwidth as you think, because I'm going to throw away half of it. And if you then have something else, which is a struct, basically, float 3, but you're only using the x's for a particular access, you're actually wasting 2/3 of your bandwidth. So if you have a problem and you have a way where the default is you don't actually know which part of memory you're going to access. Right? You have to think about, is there an easy way, a low overhead way for me to reorder my threads, or how I assign work to threads to make it reordered, to make it more ordered, I should say, more coherent. Particularly, several people have kind of asked questions about MP2 part 3. And this kind of comes up if you do different, there's lots of ways to approach that problem. Some people have been worried about that they're too slow, or why aren't they faster. And if you think about how you're accessing memory for certain ways, you will see that some of these ways are better because of memory access behavior and coalescing. So again, there's no way to get around it, that it's just just a random lookup in a hash table, or a tree or whatnot, so be it, right? You'll still get effectively a lot more bandwidth out of the GPU than you probably would out of the CPU, but you will be quite a way off of the peak bandwidth that is on the box, because effectively you're loading up 32 bytes, using 4 of them, and throwing away the other 28. So kind of one common pattern I've seen a lot and is that people are working on something and they're porting from the CPU, and they like to work on, they have structs, or in this case a record, which just keeps everything that you're going to work on in one given point together just for simplicity. And so you're porting that to the GPU, so you have the version of it on the GPU, and you've CUDA-malloc appropriate size. And if you go access it this way, if you access any particular value in that record struct, you're going to be effectively wasting 2/3 of your bandwidth. So this is this pattern, kind of this, having a big array, and each element of that array is some struct where has everything that you need to be working on, is usually called array of structures, or AOS. So if you invert that pattern, this is called structure of arrays. So they basically say, I'm going to have each of my elements be its own array, and then overall I'll have a struct which just holds all of these arrays. And again, you have the version for the GPU. And so if you go and access these, what will happen here is, again, you're going to be only effectively using every third word, because a struct is basically laid out contiguously in memory. So it's going to be 12 bytes, and you're going to be using 4 of those. And so again, it's effectively only 1/3 of the bandwidth is used. If you're doing it this way, right, this array keys is just a normal array. You don't really care about what it overall represents. And so if you just access it here, with your thread ID, it's going to be, maximum bandwidth. And you can also think of this in terms of, like, if you have matrices or other kind of high-level structures, the pattern you're accessing them in matters in terms of if you're going to have, contiguous accesses which are right next to each other, or stuff, axes which are very far apart, and you're going to be wasting bandwidth. So if you have a problem which is, doing a lot of read modify writes and kind of doing a little math or whatever in between, and so you're probably bandwidth bound, or you're certain that you're bandwidth bound, then you need to think about these kind of things, because it can be a factor of 16 in terms of how much bandwidth you can get. So again, this is just if the access pattern is obvious. Sorry, question?
If you had a situation where you knew that your kernel was going to access all the different fields or values in a struct,
sure,
then could there be maybe a performance benefit to using an array of structures, because it's more likely that you're only going to have to load the whole struct once? Or is that?
So yes, there There can be cases where having a struct which you can just load up once and then have it in registers or shared memory is the right way to go. The problem is if you let me just go back for 1 sec to this thing, how the compiler translates. If you just say, I want the whole copy of this whole struct in registers, how the compiler translates that into actual load and stores is very much dependent on lots of things. Size and shape of your struct, literally how the compiler is feeling about lots of other things which you have no clue about. So it might translate that into basically load, key, then load value, and then load flag, which effectively is again back to badness. Now, if you've loaded, so again, that only matters if you kind of load it up once, do very little of it, and then throw it away, or if you load it up once and then do a lot of work on it, right? Yeah, you've wasted some bandwidth, but it's not the main part of your computation, so it doesn't matter. But if you want to load up the whole struct, you're somewhat at the mercy of the compiler to do the right thing, which can often be an iffy issue. So even then, it's sometimes better to do the structure of arrays thing. But it really is a case-by-case kind of issue. Sorry, question?
Does the CUDA-malloc return aligned pointers always?
The question is if the CUDA-malloc returns aligned pointer, which basically is that, you know that your array starts at the right offset, and the answer is yes, it does.
And in the case you brought up, isn't there the memory coalescer that would, even if you issued those 3 loads, if they're in consecutive addresses, wouldn't a thing a little higher up on the memory controller side do the right thing there maybe?
Right. So the question of, isn't there extra hardware which basically kind of regathers, recoalesces those requests? And the answer is, yeah, there is extra hardware, but there's lots of ways where this can go wrong. So, let's say you've written it this way. Let's say you have 3 consecutive load instructions, right? It's from the same thread. As I, told you guys the last couple of times, there's a lot of threads, like 1024 per SM, and there's a lot of SMs per chip. And the scheduling is, to first order, you can think of it as random. So even though the loads can be consecutive, the amount of time when they actually execute can be pretty arbitrary. And so if the hardware cannot wait an arbitrary amount because it's like, oh wait, thread 0, I know it has 2 more loads coming, I have to hold on to this one request.
So it's not in shared memory, it won't find a cache hit.
Yeah, so there's on the cards which are in the PUPS cluster, there's no caching going to global memory. On Fermi there is, and so the caches will naturally do some of that, what you want, but again, it kind of depends on the access pattern. And because you have a lot of threads, if the loads are too far apart, again because of scheduling reasons, something might have evicted, the prior entry out of a cache. So it's somewhat iffy to rely on that. Right, other questions about this? So it's basically, think about this again, kind of, if you have the workload which basically does, read in several values, do their sums, do their average, write them, write that value back out. Very common, like stencil codes, and find a difference and stuff like that. Because the amount of work you're doing per load and store is relatively small, so you're probably limited by memory bandwidth. Then you want to optimize this. If it's a case that he was mentioning, you load in a struct once and then you work a lot on it, don't worry too much about it. All right, so shared memory band conflicts. So shared memory is basically what the physical array is subdivided into individual subarrays, so you can think of them that way, which each can fulfill 1 request per cycle. So if you make a request where you just write out or read in an array the same way as you would for the global memory, just by thread ID into global memory, each thread will basically go to its own bank. And so it's going to be, right, one-to-one mapping, it's fine. If you have, so that's kind of the case here on the left. Well, your left, hopefully. If you have another pattern where you're going all over the place, but it's a full permutation, that's still fine. Full performance, either way. You don't have to worry about that. What you do have to worry about is if there's this case where everybody wants to read out, let's say, element 0 and element 16 at the same time, right? Then those, for example, could map to the same subarray, and because the subarray can only, or bank, can only fulfill one request per cycle, it's going to take 2 cycles to fulfill that. So basically, you're going to have a factor of 2 slowdown. So that's kind of what this pattern here is showing. If you have something which is kind of almost worst case, where you've allocated your memory somehow so that when the threads from a single warp, and this is always just a single warp, go access things which are, let's say, a nice multiple of 32. So you want to access element 0, 32, 64, and so on. And those just happen to map to the same bank, which they probably will. Then it will, slow down by, however many threads go bang on one piece of hardware. So this is kind of important if you're usually when you have like, a matrix or something like that, and you want to do row major versus column major accesses, and you've brought in a, part of the matrix, a tile, which is a nice multiple of 2 in row and width, and height, sorry. And then these patterns are, kind of what I've seen are the most often which they occur. You kind of need to think about that a little bit. So if you know ahead of time that your stride in which you're accessing your array, or if you have a 2D array, is a nice multiple of your warp width, which is 32, you might be you might be suffering from this effect. And kind of there's lesser issues if you have everybody just looking at even values or odd values in your array. Overall, unless you're really kind of in the worst case access pattern where basically 32 threads are all going to the same bank, shared memory will still be a lot faster than going to global memory. But if you spent the effort to bring in data into shared memory because you want to have that extra speed and don't want to suffer from the overheads of global memory, like having to read in memory in chunks, then do think a little bit about in what patterns you're accessing shared memory as well. And so a couple of tricks to know if you're suffering from this is from one of our colleagues, Paulius at NVIDIA, is to basically say, well, I don't know what my pattern is. It's going to be data dependent. And you basically can say, well, I'm going to replace my shared memory accesses, even though it's going to be the computation is going to be wrong. I'm going to replace them with some offset, some index, which is shared across, let's say, all the threads in a warp or thread block, which means that everybody's going to access exactly the same value. So broadcast of a single value, those work fine. It's just if you want to access 2 different values in the same physical bank that you're going to have trouble. So you can basically say, okay, I'm going to replace all my shared memory lookups with this one value so I know it's full speed, and see how much faster you go, even if you have the wrong result. And if the difference is very small, then you can say, I can ignore this. And if the difference is large, then well, maybe I have to think about this some more. Obviously, for writes, this is not so much possible because writes do have to go one after each other. You can't just, the hardware won't magically takes care of that. Yeah?
That wouldn't work for Fermi due to the caching, right?
So the so Fermio has regular caches which don't have the same issue as shared memory. They have their own issues. You will not suffer from band conflicts. You will suffer from, well, tag conflicts, let's call it that way. So if you want to know more, we can talk about it offline, but in effect, no. So kind of additional memories. We've talked a lot about global memory and shared memory. One which Jared has already mentioned, which is constant memory, and he's already kind of explained. The other thing, which is kind of this feature from graphics, which is called textures. So textures, to give you the kind of very high-level overview, is basically 2D array. You can think of them as images, which are accessible in the graphics pipeline in a read-only fashion. And so there's hardware to support those axes, namely what's called texture caches. And so that feature is also accessible through CUDA. We didn't kind of show you that in the examples because it's kind of special purpose. But if you go into the programming guide, there you'll see examples how you can basically say, I have this regular array which I've just CUDA malloced, and I can basically use it with a texture, and then I can get to use the functionality of a texture caches. Now the issue here is that texture caches are somewhat specialized, so where they actually make sense to use is also somewhat specialized. So if you know that your access pattern will be random and but has some kind of structure to it, high-level structure, they might help, but they might not. So overall, it's look into it if you really want extra performance, and come talk to us, and we'll kind of probably can tell you when it will work and then when it won't. I'll leave it at that. And constant memory, so Jared told you most of these things already last time. The one thing I'm not sure he got to mention is that because constant also has a history kind of in from the graphics side, overall it's limited to 64 kilobytes. So and that's for your whole kernel launch. So if you share one 64 kilobyte or less lookup table, which is global to all your threads, then and you access it in a way which I think Jared has explained to you last time, then constant memory might be of interest. But because of 64 kilobytes, there's somewhat limited use. All right. So with that, enough about memories of various kinds. Let's talk about control flow. So I've talked to you already about what happens if you have a branch statement where some threads want to go one way and some threads want to go the other. So just to recap, if you have an if then else statement and even threads in a warp want to go one way, odd threads want to go the other way, effectively the hardware will basically execute the even threads first, put them to sleep, and while the odd threads are sleeping, then activate the odd threads, execute them while the even threads are sleeping, and then activate everybody again and keep on executing. So if you can, and you have a lot of this kind of branching, think about how you can restructure how you assign work to threads so that bigger groups of threads, have a bigger chance of doing the same, going down the same path. But what I really wanted to talk to you about today is this pattern, which hopefully some of you will recognize from MP1 Part 3. So each thread basically goes off and does a certain amount of work, and that work is the amount of work you have to do is data dependent, right? Each thread will say, well, what's the difference between these two values, and will have to execute that loop so many times. So if your data just happens to be such, and there are certainly workloads like that, where the great majority of your threads need to execute that loop 10 times or around, that number, and some others need to execute it 1,000 times, what's going to happen is that that one thread, which needs to execute that loop 1,000 times, will basically be dragging along everybody else. This goes back to the SIMT hardware that we talked about in the first couple of lectures. That means because this group of thread 32, which are in a warp, are only executing a single instruction, the 31 other threads, which are all basically done, will be waiting for the last thread to just keep on iterating until it's done with the loop, until they can get to here and finish up. So this is a very kind of data-dependent problem. If you know you have these kinds of things, like you're working on different partitions, you've chunked up your overall global work into different size chunks, which are very dependent on how the data actually looks. Like let's say you want to construct trees or hash tables or lots of other things. And some of those partitions, or most of them, are small and some of them are large. This might be an issue. Think about other cases where this could be an issue. If you have this kind of access pattern, what you probably want to do is basically limit the number of iterations to something which is large but somewhat reasonable. And that basically means if and have some code which basically cleans up after the long-running threads, because you've basically cut off threads which would have run for 1,000 iterations, but you've cut them off at 100. Right? They're obviously not done. So you basically need to figure out which one those are and finish them off. And actually, Jared will show you a very, very nice and fundamental pattern next time, how you can do that and still have kind of efficient execution of these stragglers, if you want to call them that way. And another way to do it is not as nice. Well, it depends on kind of what you're doing. Is to flatten the peaks, which is basically if you have this very spiky kind of distribution of work, then you can say I'm going to have each thread work on multiple data items. And that means that you're just going to try to average out the big spikes with lots of little values, so that overall you don't suffer as much from the load imbalance of one thread dragging everybody else along. Does that make sense? Okay. So with that, we get into occupancy, which is a tricky issue, which also has kind of come up in MP2, especially with shared memory. And here, just a very quick reminder why we care about occupancy. I've kind of pointed this out to you in previous lectures. It's basically if you have, let me back up. The hardware, each streaming multiprocessor, you can have up to 1,024 threads active. And I've kind of told you, well, why do we need this many threads? It's because we want to be able to switch in. You always have work available. So if some threads stall, like again in this example, which I showed you previously, these yellow threads here stall, then you can swap in other ones to do work while they're stalled, and once they're done, stall, and then you can continue working on them. So this is basically to make more effective use of your hardware and get the maximum throughput. So yeah, I think I've already mentioned this. So what determines occupancy? We kind of alluded to the fact that in GPUs, you're effectively only using as much resources as you really require, as opposed to CPUs. In CPUs, you have a fixed number of registers, 8 or 16 or 32, depends on the architecture. And each thread will have all of those registers available to them. On the GPU, you basically figure out how many registers do I need, and you get that many. How much shared memory do I need, and you get that much. And depending on how much you need, that means that also influences how many threads actually can be running. So just as an example here, so you have a certain number of registers for each a streaming multiprocessor and a certain amount of shared memory. And so if you have some program, some kernel, and it has a certain number of threads, and each thread has a certain number of registers, then and a certain amount of shared memory. So then you're going to basically come in and say, I'm going to ask for this many resources. This is no problem, right? We have plenty. So thread block 0 can go and can start executing. And the next one comes in. It's same thread block, same kernel, I should say, same requirements. This one is fine too. And then the last one comes in. And as you can see, in this case, you're using all the registers that you have, but you're only using a relatively small fraction of shared memory. And that's fine. But that's the kind of, so what's limiting you in this case is how many registers do you have, right? If you had 3 times as many registers, you could run more thread blocks and basically have a higher likelihood of maintaining peak performance because you can have a bigger pool of work among which to choose at any given point in time. But if you have a different program, a different kernel, then you might have, need a lot of shared memory for each thread block for whatever reason. And in this case, you will max out with a smaller number of active thread blocks and active threads and potentially have lower performance. But what you should really notice here is that you didn't actually fill up shared memory. And that's because you can only allocate a whole thread block. So if the amount of shared memory or registers or what have you doesn't nicely divide into what you have available, there's going to be some left over. And I'll show you some examples. So and the last limit is basically that you can only have 8 thread blocks per cycle. And actually, wait, do we have? So yes, let's skip right to here. So those of you who have started MP2 might have noticed that our makefile has some extra flags. One of those, hopefully it's still in there, is passing dash x ptx as and dash v, and that basically tells the compiler, please be somewhat chatty. Tell us for each kernel how many resources it actually uses when you're all done with it. And then you can take those numbers and there's an Excel spreadsheet which you can download from the internet, which actually you can tell you what your occupancy will be. So you can figure out kind of if this is a problem or not. And you don't happen to have a shell which I can actually show them running on VCC, right?
I should.
Okay. Why don't you? So do you have the solutions for MP1, for example, so we can?
I do not.
Okay, or.
But you can.
Improvise. Right. So. Okay, so these are just the reference versions. So in this case, we unfortunately basically have no actual active kernel in there since Jared only has the kind of code we gave you, I guess. So you won't see this. Do you have any actual CUDA code somewhere which I can compile? No? Okay, well, we'll skip that part. We'll skip that part of the demonstration. So let's go. No, not there. So the output will basically tell you the number of registers you have per thread, and it will tell you in bytes SMEM, that's shared memory. And you can take those numbers and plug them into this Excel spreadsheet, which you can find online. Just Google CUDA occupancy calculator. And so let's say we are running on, this will be interesting. Is that it all? Yeah. Okay, so let's say in this simple example, we have a simple kernel which uses 8 registers. So I'm not sure if you can read it. This might be too small. So what you'll get, is there a way for you to zoom in? If not, I'll go back to the, okay. I guess too many. You know what? I'll just go back to the slides. It's getting too. So what you'll see kind of in the, you know, what the hell? Upper left-hand part is these values. So you can basically enter here how many threads you have per thread block, you know, how many registers the compiler will have told you, and how much shared memory you use per thread block, the compiler will have told you as well. And then it will spit out, and this number up here, this is basically what generation of card you're using. So you all, if you're running on the PUPS cluster, are using 1.3. So then it will spit out something like this. And these are kind of all hard-coded numbers for that particular generation. But if you look up top, it will say active threads per multiprocessor, so per SM. And we've told you that 1,000 or 1,024 is the actual maximum imposed by the hardware, but we only have half of those threads available to us. And so we have 4 thread blocks active and so on. So as you change your numbers, those numbers in blue will also update to kind of tell you where you're at. And almost the most interesting part is the graphs, which are shown, even though they're kind of ugly, on the rest of the spreadsheet, which basically tells you, as a function of all these different variables, what happens to your occupancy if you decide to change your program. So here, this is threads per thread block, so thread block size. So you can see here that even though we chose a certain thread block size, if our the amount of shared memory per thread block is constant, then we should have actually chosen you know, a different thread block size and gotten a higher occupancy. Now in this particular case, the difference here is very small, so it probably doesn't matter. But what you might see here is if for some reason we have fewer registers, then you actually can have higher occupancy. And lastly, down here you can see that shared memory is actually not, you're using very little of it, so it's actually not an issue at all. So let me try to go back here. So I'm not sure, does anybody, can you guys read the actual numbers in the on the spreadsheet? No. Okay. So I'll just have to just trust me when I tell you what's what. So command plus. Yeah. Control zoom. Of course, I'm not a Mac person. Do you know? Oh. There we go. Wonderful. Okay. So if we change, if you have a more complicated program, so by the way, if you guys have Wi-Fi access, you can download this thing in like 5 seconds and play along. But so let's say you have a more complicated kernel. Let's say you have 24 registers. And then you want to have command zoom, wait, control zoom out. Okay, so I've just increased the number of registers, and you might have noticed that the curves here all went down, right? So if you have a more complex kernel, you will have fewer active threads overall because you only have a finite number of registers. But kind of what I really want to show you is, because it applies to MP2, is what you want to do often is the amount of shared memory is not constant, but is a function of your thread block size. So now, okay, so now what should happen here if I cut the thread block size in half is, you see you can jump around. So basically, Excel will evaluate that function at all, possible inputs. So the shared memory usage will scale with your thread block size, for example. And so what you can see here is that there's really some weird-ass peaks and valleys. And basically what's happening is this having a nice something which fits nicely inside of your resource requirements or not. So if you happen to have a program where you use a certain amount of shared memory per thread, and you should be all working on such a program right now for MP2, then you can get into this case where you just chose a default thread block size, and you just happen to end up in a valley as opposed to a peak. So it might be useful, at least as an exercise, to look at the output from the compiler, which it already should by default be that chatty, so you should have those numbers, plug them in, and see where your solution is at. If the peaks and valleys are very big, because it just so happens to be, then it actually might make sense to kind of play around with thread block size and find something which works better. If the peaks and valleys like here are pretty small, so if you're just in this range, you don't really care. But if you suddenly for some reason end up down here, right, you might want to dial it back to somewhere here, just as a hint. So okay, was that kind of understandable how that works? Anybody have any questions? This is the first time we tried a live demo with Excel, I guess. Okay, with that said, let's, of course I need to zoom back out, don't I? So the other thing I haven't told you is, so I told you the compiler will give you a certain number of registers, and it will also show you this graph where well, if you had fewer registers, it would be better sometimes. And that's not very helpful if you don't know how to influence that register count. So one way is to just go back into your code and say, well, I'm just going to make it simpler, because usually simpler, having fewer variables means fewer registers, although sometimes it doesn't. It's kind of weird in that way. But you can kind of tell the compiler, hey, I really, really would like to have 24, not 25 registers, by passing it, this flag, this option, and setting it to whatever value you want, and it will stick to that limit, always, or at least mostly. And it will push down the register count, to what you ask for. However, this is not magic. This is not magically you get to run faster. The same amount of state still has to be stored. So what usually happens is the compiler figures out, hey, I have too many values for the registers I'm given. I'm going to be, spilling some of them into memory and then reading them back in. And we just told you several times over in the last couple of lectures that that's slow. So if you push the compiler to, save me 10 registers, it will do that, but it will just spill 10 values, which it will read very often into memory, and you will have a really big slowdown. But if you are at the very edge, in these spreadsheets that you just need that one fewer register, sometimes that can work without having a big performance impact, and you get a net gain. Again, this is something to play around with, kind of once you've optimized for memory bandwidth and enough parallelism and all that, then you start to think about, okay, what is my occupancy? Not before. This is kind of the last thing you want to tweak, because it might give you extra 20 or 30%, but it will certainly not give you, the 10x or 100x that the right parallelization and the right ordering of work to threads gives you. All right. So that is hopefully more than enough than you wanted to know about how, to tweak the very low level your code to get more out of the hardware. The last thing I should mention here is kernel launch overhead. So if you launch a kernel on CUDA, we kind of walked you through at the high level what that means. Basically, the CUDA runtime packages up the arguments and the kind of config of your grid on a CPU, sends that over to the GPU. GPU then, has dedicated hardware which broadcasts that information to all the streaming multiprocessors, and they start to request work, get work, do all the work, inform the hardware again that they're done. When everybody's done, the CPU gets informed, hey, I'm all done. This is not completely free. Actually, it's, overhead is very small for if you have reasonable amounts of work, but if you do very little work kind of per kernel, which you might, there's very good reasons if you need to do that, you will notice that there is kind of a finite number below which you cannot push a kind of kernel launch. And so if you're working on little data and doing little per thread, this might hurt you because you're basically paying the overhead again and again and again. If you're, have basically maxed out your grid size or you're doing quite a lot of work per thread, you will never notice this. It's a very small number, but it is there. So, but if it is kind of, this is an issue for you, then try to think about, well, why can I only do very little amount of work per kernel launch? Is there something inherent to my algorithm, or can I change something? And so if it is because kind of the amount of the work is unstructured, so you need to be able to say, well, now work on this segment, which is this size, and now work on that segment, which is that size, and it's kind of not obvious right up front, how big these segments will be because it's dependent on your data, then we'll be talking about ways where you can basically combine all of that stuff into nice big kernel launches in the next couple of lectures, starting Thursday with Jared's talk. And if it's something because you just literally need to communicate values between arbitrary threads through global memory, there's no way you can package it up and it can go through shared memory. There are certain ways where you can get around that. They're expensive, or which I should say, they just require work on the coding side, but they are cheaper than just launching lots of threads, lots of kernels with very little work. If you have something along those lines, come talk to us, and we'll kind of show you one off. It's not something which everybody should be doing, since it is a lot of coding overhead and you need to think about even more stuff, but it might be interesting and useful for certain people. Okay, so with that, yeah, sorry, there's actually one more very common case, which is you have a little bit of data which basically tells you whether you are done or not. Do I need to iterate one more time, or have I converged? Have I found whatever I'm looking for? Is my solution good enough according to some criterion? And often people do all this work, compute something, read back out to the CPU, and that tells it, yeah, do it again, do it again, do it again, do it again. If this is very common and you do this like 100 times, and you're doing little work per step, then think about actually having that control decision being done on the GPU, even if it's completely serial work, because just copying a little bit of data back to the CPU and then having the CPU just look at that and then launch on the kernel could be more expensive than doing the serial work, even though it's slow and even though it doesn't utilize the GPU well on the GPU. So kind of don't underestimate how fast the GPU is, even a single thread, if you need that kind of work. So let me kind of, again, remind you of the most important things. First, measure some more, and measure even some more. So you know where your time and your effort is going. And only optimize what you need to. Don't think you need to optimize everything. don't think you need to invest the same amount of effort into optimizing or changing your code for every part of your code. Some pieces will take 0.1% of your time, and some pieces will take 50% of your execution time. And so focus on the big chunks. And often you'll have, oh, I know my bottleneck is X. That's what's limiting me. I'm going to do this change, and I'm going to use 5 times less of X, whatever that is. I'm going to do so much better. My code should run 5 times faster. And then you actually make that change, and it just so happens it only runs 50% faster. And you're frustrated because what the hell happened? Or, and very often what you have is a series of bottlenecks. Yeah, right now, what's limiting you is X. But right behind that is Y and then Z. And so you will very often get kind of a speed up which is smaller than you expected until you go back in and figure out, oh, I was limited primarily by X to this speed, and then by Y to this speed, and then by Z to this speed. And only if you've eliminated all 3 do you start to go really fast. So just be aware that happens often. It's not just the GPU, also for CPU, kind of anything you do in software and optimization. Basically, actually, most of the things I've told you apply just as much to the CPU, certainly the measure part. If you want more speed, first think about parallelism, then think about kind of, ordering, and then start to think about these low-level issues. Yes, a question?
Is there any profilers for that?
So there is a profiler for CUDA. It, however, gives you back some very low-level information. It doesn't give you back in terms of like where your time goes right up top, unless I'm mistaken and the newer version does that. Do you remember? The newer version might give you more information, but we haven't played with it ourselves, so we couldn't tell you. But especially because profilers are kind of usually tied to a platform, if you just put in simple timer code, which is nicely kind of encapsulated, we tried to kind of show you in the MPs one way to do it. You can certainly do it different ways. Then you know for sure that whatever the errors are, they're yours. Usually these profiles have their own kind of issues, and so you need to keep in mind both what's going on in your code and what potentially is going on in the profiler. But they can be very useful if you really don't know what's going on. So there's a low-level profiler, just to repeat, but and you can find it on the web. All right, and with that, I've given you lots and lots of information. Any questions? No? So Niels actually, sorry, there's a question.
Is there a better way to profile than just the high level, like CPU size, kernel by kernel?
So if you want to look at kind of where the time is going inside of a thread, there is a clock function, which I think is just available by default if you're programming in CUDA. And that will basically give you back, if I remember the definition correctly, basically kind of an arbitrary number, which just happens to be some cycle counter. And so so a single call to that will not help you at all. But if you kind of call that in the beginning and call that in the end, the difference will be meaningful to some extent. The issue is, right, that's for a single thread. And so with scheduling, that might not tell you that much, because the hardware scheduler might have decided that that thread, the warp which that thread is part of, just happened to take an extra long time. So if you use that, then kind of look at the results over lots of threads, and also be aware that there's some overhead in calling that, very similar to what if you would do something similar on the CPU. I want to say there's one more low-level function, but I'm blanking. Do you remember?
You do things like just count the number of flows you do by instrumenting your code.
Sure. You can certainly count, well, the profile actually will give you that. So yeah, so just calling clock inside of your threads will give you these arbitrary numbers, the difference of which will actually tell you something about how many clock cycles something took for the thread, but it doesn't mean that the thread was active at any point throughout that range. More questions? Did you have? No? All right.
For more, please visit us at stanford.edu.